Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya, Sagar. In this course, I will deliver my lecture on Amphibolite Facies. I will cover this topic in three parts. In part 1, I will proceed under the following heads: introduction, mineralogical characteristics, subdivision into zones and subfaces, stolite zone, stolite almandine subfaces, and summary. Hope it will be useful for you. On the basis of pressure and temperature, we can divide the metamorphic facies into three types, mainly A. Facies of low pressure, B. Facies of intermediate pressure, and C. Facies of high pressure. Maya Siro originally recognized three different facies series. First, a geolite, prehenite, pumpelite, blue schist, eclogite type. Second, a typical Barrovian type characterized by green schist, epidote amphibolite, amphibolite, GEOLOGY type characterized by paragenesis of kyanite, selemonite type. And third, an Abukama type of green schist, amphibolite, GEOLOGY characterized by andalusite, selemonite type. The Abukama type is named after the Abukama region in Japan and is similar to the Boken type of the Dalardian. The facies of intermediate pressure are listed on the screen in order of increasing temperature and pressure of metamorphism. First, geolite facies, second, green schist facies, third, amphibolite facies, fourth, GEOLOGY facies. The amphibolite facies derived its name from the occurrences of hornblende plagioclase, anorthite 25 to 40%, paragenesis in the metabasic, gabbroic or basaltic composition, rocks of regional metamorphism. The diagnostic mineral assemblages restricted to this facies are hornblende, plagioclase, anorthite more than 15%, almandine and hornblende, plagioclase, anorthite more than 15% with epidote. The appearance of any of the following minerals is decisive for the identification of amphibolite facies, that is stolite, gracilurite, andradite, diapsite, cummingtonite and anthophyllite. Furthermore, white mica, which was approaches phensite in composition in green schist facies, changed to muscovite. Abundance of almandine, stolite or kyanite and absence of corderite and andalusite distinguish peltic assemblages of the amphibolite facies from those of the hornblende, hornfels facies of low pressure metamorphism. The amphibolite facies has a wide distribution in the Precambrian terrain and in the deeper part of the orogenic belts. The classic occurrences of the amphibolite facies is in the Barrovian zone of medium to high grade from the stolite isograde onward. The diagnostic mineral assemblages restricted to the facies are hornblende, plagioclase, anorthite more than 15%, almandine and hornblende, plagioclase, anorthite more than 50% with epidote is the diagnostic mineral assemblages of basic rocks. The peltic schist in this facies contain biotite and muscovite with almandine garnet, stolite, kyanite, selemonite. Kyanite with potash feldspar appear in the high temperature part of this facies. Anthophyllite, cummingtonite or gedrite occur in magnesian, schist and ultramafic composition. In calcareous rocks, the pair diapsite, epidote, gracilurite and diapsite, calcite, gracilurite are characteristic. The amphibolite facies is characterized by the absence of chloritoid and chlorite in the presence of muscovite and quartz and talc. Francis in 1956 recognized three subfaces in peltic rocks of the amphibolite facies. These are stolite zone, kyanite zone and sillimanite zone. The three subfaces correspond to the zone of stolite, kyanite and sillimanite of the Scottish Highland. Turner in 1968 and Winkler in 1976 added a fourth subfaces named sillimanite almandine orthoclase subfaces. These are listed in order of increasing metamorphic grade, temperature and pressure. The transition from green schist to amphibolite facies is best recognized by the diagnostic first appearance of stolite and disappearance of chlorite and chloritoid in the presence of muscovite and quartz. The reactions are: reaction 1, chlorite plus muscovite plus almandine garnet give rise to stolite plus biotite plus quartz plus water. This reaction carried out by Hosek 1969, 540 degree centigrade 4 kilobar, 565 degree centigrade 7 kilobar. Another reaction, chloritoid plus kyanite give rise to stolite plus quartz plus water, 540 degree centigrade 4.5 kilobar, 575 degree centigrade 8 kilobar, carried out by Hosek 1969. Richardson 1968, chloritoid plus quartz give rise to stolite, almandine garnet plus water. Reaction number 3, temperature 15 to 30 degree centigrade higher than reaction 1 and 2, carried out by Ganguly 1969. Presence of stolite along with kyanite is diagnostic of this facies. Stolite appears in those rocks that are richer in Al2O3 and FeO and poor in alkalis, as shown by Hosek 1967. Important reaction: the impure calcareous rocks, diopside and gracilorite form by the following reaction. Tremolite plus calcite plus quartz give rise to diopside plus CO2 plus S2O, reaction number 4. Another reaction, epidote plus albite give rise to anorthite rich plagioclase. Next reaction, epidote plus quartz give rise to gracilorite plus anorthite plus water. Next reaction, epidote plus calcite plus quartz give rise to gracilorite oblique andradite plus CO2 plus S2O. 500 degree centigrade 2 kilobar, 575 degree centigrade 4 kilobar by Nice 1973. Furthermore, anthophyllite appears in magnesium assemblages. Talc give rise to anthophyllite plus quartz plus water, reaction number 8. For pure Mg system, the above reaction has been investigated by Greenwood 1963, who found the equilibrium temperature at 607 degree centigrade 1 kilobar, while for a system in which Fe-Mg ratio is 6:4, the reaction occur at much lower temperature, for example 520 degree centigrade 1 kilobar by Henrichsen and Sefford 1965. Anthophyllite also appear by the reaction tremolite plus chlorite plus quartz give rise to hornblende plus anthophyllite plus water. Reaction number 9, 560 degree centigrade 2 kilobar, carried out by Chaudhary and Winkler 1966. Peltic rocks. Number 1, kyanite plus stolite plus biotite with muscovite quartz plagioclase. Second, stolite biotite almandine with muscovite quartz plagioclase. Third, almandine biotite with muscovite quartz plagioclase. Quartzo-feldspathic assemblages. Assemblage 4, biotite muscovite microcline with plagioclase and quartz. Basic assemblages. Number 5, hornblende plagioclase almandine with epidote quartz plus minus biotite. Number 6, hornblende plus plagioclase with epidote plus quartz plus minus biotite. Number 7, hornblende plus diopside plus plagioclase with epidote plus quartz plus minus biotite. Derivatives of the basic rocks are amphibolites. Many of them are garnetiferous. Coexistence of the plagioclase anorthite 25 to 45% with epidote is common in these rocks. Ultrabasic or magnesium assemblages. Number 8, cummingtonite plus hornblende plus albendine. Number 9, cummingtonite, anthophyllite, tremolite, calcareous assemblages. Number 10, calcite, diopside, gracilorite plus minus quartz. Number 11, calcite, diopside, tremolite plus minus phlogopite. Number 12, diopside, gracilorite, plagioclase plus minus phlogopite. Note, in such rocks, sterolites appear under high to medium and even low pressure condition. By the reaction, chloritoid plus kyanite give rise to sterolite plus quartz plus water. Reaction number 2, 540 degree centigrade 4.7 kilobar, 575 degree centigrade 8 kilobar, carried out by Hosek 1969, Richardson 1968. Another reaction is chloride plus muscovite give rise to sterolite plus biotite plus quartz plus water. Hosek 1969, 540 degree centigrade 4 kilobar, 565 degree centigrade 7 kilobar. In this lecture, I will proceed under the following heads: kyanite almandine zone and sillimanite muscovite zone. Hope it will be useful for you. Try to be regular in course. Rock of these subfaces resemble those of the sterolite almandine muscovite subfaces, except that sterolite in kyanite almandine muscovite become unstable and the pair kyanite almandine coexist together. This corresponds to the kyanite isograde of Barrow. Sterolite is now no more stable. It reacts with quartz in the presence of muscovite to form almandine plus kyanite and plus minus biotite. Sterolite plus muscovite plus quartz give rise to kyanite plus minus biotite plus almandine plus water. At 575 degree centigrade 2 kilobar, 675 degree centigrade 5.5 kilobar. This reaction was carried out by Hosek 1969. The reaction has not been revised by Hosek and probably the temperature given are higher. Thus, the disappearance of sterolite provides the only possibility of differentiating between the subfaces oblique zones 1 and 2. It is evident that the critical association of kyanite plus almandines are now possible, which gives the subfaces its name. It is also obvious that in these subfaces, kyanite is much more common as compared to the sterolite almandine subfaces or sterolite zone, because the range of chemical composition from which kyanite now form is much larger here. The characteristic peltic assemblages are: number 1, kyanite almandine biotite with muscovite plagioclase quartz. Number 2, kyanite biotite with muscovite and quartz. Number 3, almandine biotite with muscovite, quartz and plagioclase. Other assemblages are same as the sterolite zone mentioned already in previous lecture. Quartzo-felspathic assemblages. Number 4, biotite muscovite microcline with plagioclase and quartz, basic assemblages. Number 5, hornblende plagioclase plus almandine along with epidote biotite quartz. Number 6, hornblende plus plagioclase with epidote quartz plus minus biotite. Number 7, hornblende diapside plesioclase with epidote plus minus biotite plus quartz. The derivation of basic rocks are amphibolites. Many of them are garnetiferous. Coexistence of plesioclase, anorthite 25 to 45%. The epidote is common in these rocks. Ultrabasic / magnesium assemblages. Number 8, cummingtonite, hornblende, almandine. Number 9, cummingtonite, anthophyllite, tremolite, calcareous assemblages. Number 10, calcite, diapside, gracilorite plus minus quartz. Number 11, calcite, diapside, tremolite plus minus phlogopite. Number 12, diapside, gracilorite, plesioclase plus minus phlogopite. The mineral assemblages of these zone / subfaces are similar to the kyanite zone here. Here, kyanite is replaced by higher temperature Al2SiO5 polymorph sillimanite. Replace kyanite by sillimanite in all diagrams. This has been experimentally studied by several workers. Amongst them, the coarse and triple point of Al2SiO5 by Holdaway 1971 is widely accepted. The conversion of kyanite to sillimanite take place with the stability range of muscovite plus quartz so that muscovite can coexist with sillimanite. Mineral assemblages. The typical peltic mineral assemblages is number 1, sillimanite, almandine, biotite with muscovite, quartz and plesioclase. Number 2, sillimanite, biotite, muscovite with plesioclase and quartz. Number 3, almandine, biotite with muscovite and quartz and plesioclase assemblages. In quartzo-feldspathic, basic, calcareous and ultrabasic rocks are same as in the kyanite, almandine, muscovite subfaces. Quartzo-feldspathic assemblages. Number 4, biotite, muscovite, microcline with plesioclase and plus minus quartz. Basic assemblages. Number 5, hornblende, plesioclase, almandine with epidote plus minus biotite plus minus quartz. Number 6, hornblende, plesioclase with epidote plus minus quartz plus minus biotite. Number 7, hornblende, diapside, plesioclase with epidote plus minus quartz plus minus biotite. Derivatives of basic rocks are amphibolite. Many of them are garnetiferous. Coexistence of plesioclase, anorthite 25 to 45 with epidote is common in these rocks. Ultrabasics or magnesium assemblages. Number 8, cummingtonite, hornblende, almandine. Number 9, cummingtonite, anthophyllite, tremolite, calcareous rock assemblages. Number 10, calcite, diapside, gracilorite plus minus quartz. Number 11, calcite, diapside, tremolite plus minus phlogopite. Number 12, diapside, gracilorite, plesioclase plus minus phlogopite. Muscovite, which was present throughout the range of metamorphism from green schist to sillimanite muscovite zone of the Amphibolite Facies, now becomes unstable. It is with this breakdown of the muscovite that the sillimanite orthoclase zone begins. The following reaction take place. Muscovite plus quartz give rise to orthoclase plus sillimanite plus water. Reaction number 10, 595 degrees centigrade 1 kilobar, 640 degrees centigrade 2 kilobar by Day and Chatterjee 1974. Microcline give rise to orthoclase, that is higher temperature polymorph. With this reaction, sillimanite is much more common as compared to preceding zone and now it coexists with orthoclase. The KAlSi3O8 polymorphs microcline is also transformed to higher temperature orthoclase. Furthermore, under the pressure and temperature condition of this zone, partial melting or anastasis of peltic rocks take place as demonstrated experimentally by Tuttle and Bowen 1958, Winkler 1967, 1974 and others. Thus, migmatites or vein gneisses or lit per lit or injection nices are common in this facies. Mineral assemblages. Some typical peltic and quartzo-feldspathic assemblages are on the screen. First, sillimanite, almandine, orthoclase, quartz, plagoclase. Second, sillimanite, biotite, orthoclase, plagoclase, quartz. Third, almandine, biotite, orthoclase, quartz. Fourth, biotite, orthoclase, plagoclase, quartz. Quartzo-feldspathic assemblages, orthoclase, plagoclase, biotite, almandine, plus minus quartz. Basic assemblages, number 6, hornblende, plagoclase, almandine, plus minus quartz. Number 7, hornblende, plagoclase, diopside. Calcareous assemblages, number 8, calcite, diopside, gracilorite, plus minus quartz. Number 9, calcite, diopside, tremolite, plus minus phlogopite. Number 10, diopside, gracilorite, plagoclase, plus minus phlogopite. Ultramafic or ultrabasic assemblages, number 11, anthophyllite, hornblende, almandine. 12, cummingtonite, tremolite. Physical condition of metamorphism. The physical condition of metamorphism can be explained with the help of low and high temperature condition, and the same way pressure condition too. The lower temperature gives the idea about the beginning of the amphibolite facies, and higher temperatures give the idea about the beginning of GEOLOGY facies. Lower temperature limit. The appearance of stolite is one of the most reliable indicator of the beginning of the amphibolite facies. Stolite is formed by the following reactions. Chlorite plus muscovite plus almandine give rise to stolite plus biotite plus quartz plus water. 540 degree centigrade 4 kilobar, 565 degree centigrade 7 kilobar, carried out by Hosek 1969. Another reaction, chloritoid plus kyanite give rise to stolite plus quartz plus water. 540 degree centigrade 4 to 7 kilobar, carried out by Hosek 1969, Richardson 1968. Upper temperature limit. Upper temperature limit is indicated by the following reactions. Muscovite plus quartz give rise to orthoclase plus sillimanite plus water. 650 degree centigrade 3 kilobar, 675 degree centigrade 4 kilobar, carried out by Chatterjee and Jones 1974. FeMg anthophyllite give rise to hypersine plus quartz plus water. 735 degree centigrade when Mg ratio xmg equal to 0.6 and temperature is 775 degree centigrade. When this ratio xmg equal to 0.8, Mg anthophyllite give rise to inesitite plus quartz plus water. 745 degree centigrade 1 kilobar by Greenwood 1963. Thus, the temperature condition in the amphibolite facies is considered to be in the range of 500 to 550 degree centigrade to 750 degree centigrade. Pressure condition. The pressure condition in the amphibolite facies is determined by the triple point of aluminosilicates polymorphs. We have already seen that in the amphibolite facies, kyanite form first and is replaced by higher temperature sillimanite. This demonstrates that the lower temperature of pressure condition during the metamorphism must be above the triple point of Al2SiO5. Richardson et al. 1969, 622 degree centigrade 5 kilobar. Newton 1966, 500 degree centigrade 4 kilobar. Holdway 1971, 501 degree centigrade 3.76 kilobar. It is possible that pressure may be above 4 kilobar. Furthermore, it is estimated from the existing result that in common rocks the pressure must have exceed about 4 kilobar when almandine garnet is formed in peltic rocks. Hesberg and Winkler 1986 produce almandine garnet by the reaction Fe chloride plus muscovite plus quartz give rise to almandine plus biotite plus aluminosilicate plus water. 500 degree centigrade 4 kilobar, 600 degree centigrade 5 kilobar. Upper pressure limit. Upper pressure limit may be given by the reaction. Upper pressure limit may be given by the reaction albite give rise to jadeite plus quartz, 200 degree centigrade 7.5 kilobar, 300 degree centigrade 9.5 kilobar, chloride plus albite give rise to glaucophen. This reaction was carried out by Rover in 1972. As plagioclase is stable in amphibolite facies and glaucophen and jadeite are absent, the upper pressure limit may be around 8 kilobar. The stability of albite as well as that of garnet orthopyroxene quartz may be taken to represent the upper limit of about 10 kilobar or about crustal depth of 30 km. Thus, it is concluded that in the amphibolite facies, metamorphism take place at 500 to 550 degree centigrade to 750 degree centigrade at pressure between 4 to 8 kilobar. Dear student, today in this lectures we have discussed about the amphibolite facies part 3. I have covered this topic under the following heads: sillimanite orthoclase zone, pressure temperature condition during amphibolite facies, and summary of the amphibolite facies. On the basis of the important reaction, like sterolite is formed by the following reaction: chloride plus muscovite plus almandine give rise to sterolite plus biotite plus quartz plus water, 540 degree centigrade 4 kilobar, 565 degree centigrade 7 kilobar, carried out by Hosek 1969. And breakdown of muscovite, muscovite plus quartz give rise to orthoclase plus sillimanite plus water, 650 degree centigrade 3 kilobar to 675 degree centigrade 4 kilobar, carried out by Chatterjee Jones 1974, indicates the upper stability of this facies and also formation of the hypersthene by the breakdown of anthophyllite support the upper stability and beginning of gammalite facies. Mg anthophyllite give rise to anisotite plus quartz plus water, 745 degree centigrade 1 kilobar by Greenwood 1963. Thus, on the basis of the detailed study of different zones and also with the support of experimental data, we can conclude that during amphibolite facies, the temperature varies between 500 to 550 degree centigrade to 750 degree centigrade and pressure between 4 to 8 kilobar. I believe this lecture was useful for you. In my next lecture, I will cover sillimanite orthoclase and pressure temperature condition of metamorphism and summary. For further studies, please read the textbook, references and links given in the text.